Hello, welcome to Thermodynamics and the Great Lonsdale-Anderson video number 2. So we're going to start with defining the 4 laws of thermodynamics. My guess is they came up with 3 and then had to add the 0th, which for whatever reason needed to be a law. Because if you read through each one of these, they kind of are logical in so many ways. The 0th law says if two systems are both in thermal equilibrium with a third system, then they are in thermal equilibrium with each other. Think back to your geometry days. Pretty much the same thing. So, that's the 0th law, which essentially says if you have A and B and they are equal, and you have A and C, they are equal, therefore A, B, and C are all going to be equal together. The first law, the increase in the internal energy of a closed system is equal to the heat supplied to the system minus the work done by this. This is more of your physics, AP Physics law. So when you get into AP Physics, talk to Divine about this a lot. He will talk a lot about these sorts of things. For chemistry, you don't really need to know it, except that it is the law. But essentially what it says is, if you increase the amount of energy in a system, it is equal to the amount of heat supplied to that system, which makes some amount of sense, minus the amount of work done to either supply that heat or that heat does on the system. Law 2, when two initially isolated systems in separate but nearby regions of space, each in thermodynamic equilibrium with itself, but not necessarily with each other, are then allowed to interact, they will eventually reach mutual thermodynamic equilibrium. So what this is essentially saying is if you have hot thing here, A, and cold thing here, B, and you put them together, eventually they are going to equal a different, like a medium temperature between the two over time. And that's going to be your third combined thing, or C. So again, hot thing A, cold thing B, put them together, you get a new initial, you get new final temperature of whatever that combined temperature is going to be. Second law. Third law, the entropy of a perfect crystal at absolute 0 is exactly equal to 0. So what that's saying is that in the structure of the atom, or in the structure of a crystal, at absolute 0, it's going to be perfect. And the temperature at that place, or at that point in time, is also going to be absolutely 0.
3, 2, 1.
Welcome back. We are looking at page 912 of your textbook. So if you'd like to look at 912 of your textbook, hit pause, and then come back to 912. What you're going to be looking at is we talked about the first law of thermodynamics in chapter 5. So we're moving on from the first law. We're going to be focusing on the second law mostly in the rest of this video. And the second law of thermodynamics essentially is spelled out in this beautiful chart. And what it says is that if, for any given reaction, the delta S, or the entropy of the universe, is greater than 0, that reaction is going to happen spontaneously. If the delta S is less than 0, it's going to be a non-spontaneous reaction, or it'll go backwards. And then if delta S is equal to 0, it is reversible. The system is at equilibrium. So what that looks like in practicality is something like this. If you take this as our 0 line, and we have negative over here and positive over here. If the delta S for the universe, so the whole thing outside, is greater than 0, so if the delta S is occurring here, or the entropy is occurring here, this reaction will spontaneously take place. It will happen. However, if the delta S is less than 0, over here, that reaction is not going to take place. You will not see anything happen. Those chemicals, those formulas, whatever they might possibly be, are going to remain in stasis. And if the delta S is right at 0, it's in equilibrium. So that means all of the products and all of the reactants are equal to each other in terms of their amount of energy.
Let's do some practice problems.
Practice problems for the win. Yee! 1.
And now I'm here to do some practice problems. We are going to start with of the second law of thermodynamics. The 0th and the first we're going to ignore for right now, since what we did in the past, or what AP Physics is focusing on. And we are starting with the second law. So this first question is asking about ice spontaneously melting. So we're going from the solid state of water to the liquid state of water. The reason we're going to walk through this one is because the Check Your Learning actually references this equation and this process, and so we're just going to read through this one to start. Sit. Sorry, dog's in the room. Sit down right now. No crying. All right, so the entropy change for this process, the solid to liquid, is 22.1 joules over Kelvin. Sit down. And requires that the surroundings transfer 6 kilojoules of heat into the system. Is the process spontaneous at negative 10 degrees Celsius? And is it spontaneous at positive 10 degrees Celsius? So we're going to go ahead and use the equation delta S, so entropy of the universe, is equal to delta S of the system plus delta S of the surroundings. So change in the system plus change in the surroundings is what we're looking for the universe. The values that we're going to need to use, if delta S universe is positive, then the process is spontaneous. At both temperatures, the delta S is at that 22.1, and we have the heat of the surrounding at negative 6 kilojoules. So we're using that negative 6 right here because it's changing the heat. It's the surroundings transfer of the heat into the system. So we're going to use negative 6 kilojoules. So this was the equation we were using before for delta S. We had the entropy of the product subtract the entropy of the reactants. But this time we're changing it up to talk about the universe. So all of the entropy together with the system along with the surroundings. So this time it is a sum, not a subtraction like the last time. Instead of using delta S of the surroundings, because we don't have this right now, what we're going to plug in for that is heat of the surroundings over temperature. So this is equal to each other, so we're just going to go ahead and plug it in. So what we're trying to solve is of the universe. We have this value from the system. They gave it to us in the equation. So 22.1 is the entropy of the system plus, and then we need to solve for these right here. It gave us the negative 6 kilojoules. So if you remember, Q of the surroundings was negative 6 kilojoules. And it also gave us our change in temperature. So our temperature that we had was at negative 10 degrees Celsius, but we have to convert this to Kelvin. So if that's Celsius, we know the temperature at Kelvin would be 263.15 K. So we're going to plug both of those in to solve for entropy of the surroundings. So we put in our heat first. This time it's negative 6. I'm going to keep the decimals on. Kilojoules. And then we have over our temperature, which we've converted to Kelvin, 263.15. And so solving each of those is going to leave us with negative 7 joules over Kelvin. Don't mind the horrible J. So looking at its sign right here as a negative, we know that this isn't spontaneous. If it was a positive integer, we know that it could happen, but having a negative means it is not spontaneous. It will not happen. Since we have delta S of the universe is equal to negative joules.
Which to me makes a certain amount of sense, because if you look and just think through this, at negative 10 degrees Celsius, that's 10 degrees below where water freezes. And so it's not going to spontaneously melt at that temperature. The temperature of the surrounding, the negative 10 C, is too low to allow for water to go from solid to liquid state.
And so the second half of the problem does have us go ahead and plug in for a solid 10 degrees Celsius, so has the temperature increasing instead of it being at this negative degrees Celsius. Lonsdale, should we do that one, or do you want to just skip down to the bottom?
I think we can skip down to the bottom, but I would say pause if you are uncertain on this and work through that problem, and then think through it again logically, where we're saying at negative 10 degrees Celsius, water is not going to go from solid to liquid, but at a positive 10 degrees Celsius, above the melting point, water is going to go from solid to liquid because the surrounding heat, the area around the ice, is adding energy or adding heat into that water system.
Let's just go for it. All right, we're going to continue going with problems. We're going to use this similar equation again. Remember whenever we were doing entropy, but instead we had entropy prime was entropy of the products minus entropy of the reactants. That's what we're going to be looking at for this equation. So looking at hydrogen gas plus C2H4 producing C2H6. So we're using the same thing. This time it's talking about entropy at standard room temperature. That doesn't change anything for us, but that's what this value down here is meaning. 298 would just be standard room temperature, but in Kelvin. So we're using the same equation as before. I've got my values for products. So I believe the C2H6 has a value of 229.5, what is that, kilojoules? Is that my value for that one, Lonsdale? I honestly don't even remember.
I don't know either.
Okay, then we're going to use that value. We've got this, since in the balanced equation there's just a coefficient of 1, we don't have to do any multiplication here. But whenever we break this down into the reactants for this side, I am going to go ahead and make sure that no other coefficients are needed. So the hydrogen gas, that value I believe is 219.5, and we're going to add on the value of the C2H4, which is 130.57. Remember, none of these have to be memorized. These are all from the table. I just went ahead and had my values here.
And where would I find that table?
I would find that table at the page previous to this page. So that would be page 914. We will have it there. And 914, you can always check the appendix in the back as well. But that one is a short chart that it had handy.
G, appendix G.
Appendix G. Thank you, Lonsdale. So these two, we know we're going to add together, then we're going to subtract from this product value. And whenever we get that, overall, that equals negative 120.6 joules over moles Kelvin. Again, my J's and K's today. There we are. Let's go ahead and bounce down into the second problem so we can compare these. That one was the first, and this is the second one we're going to do. Notice there are coefficients in this one, so it's going to be the exact same process, the exact same equation, but this time we will have to multiply by coefficients. So let's start with the products over on this side. We're going to start out with delta S at room temperature is 2 times 213.8, so my 2 is coming from this carbon dioxide, and then my value there is from appendix G. Then I'm adding that by 4, since that's my water, and that would be 188.71. So again, remember the 4 is just right there. Check your charts. That's everything you've got for products. So I'm going to put a bracket around there. And then Lonsdale, if I keep going, can you still see me? Perfect. Subtract from the reactants now. So my reactants, I've got 2 CH3OH, 126.8 times 2, since there's 2 of them, plus my oxygen, which is 205.03 times, oh wait for it, oh no, I gotta check my table really fast. Oxygen is 205, so that's right. I must have just put the wrong value on mine, so it's 3. For some reason on my paper I had an 8. Maybe I just can't make 3s or 8s either. So, math, fancy. Lonsdale checks the numbers for me as always. There will be some number here that's going to be a positive. Subtract by some number here that's also a positive. But whenever I check my math, oh snap! This is the one that's messed up in the book, and we never typed it in the calculator. That's your challenge. You now have to type this in the calculator. So these two values, with those two values, a sum, same thing here, have a sum, and then subtract. I believe when this came out, it came out to be a negative. I could be wrong on that, but let's pop quiz you really fast. If it is a negative value that comes out, will it happen spontaneous or non-spontaneously? Lonsdale?
Great question.
If it's a negative.
Spontaneous or not?
What do you think, Lonsdale? What's your answer?
I think it's non-spontaneous. I think when you burn CH3OH or methanol, you need to have some sort of heat trigger to start it, and then once it is going, it will continue. But without that heat start, I don't think it's going to happen.
And so, hopefully, whenever you do the equation, you will get the correct value. It is not this. There was an error here where they did not multiply that 213 times 2. So they messed up in the book, and so that's why we don't know the answer right now. But go ahead and type it in, see if you get a positive or negative integer, and make sure you remind yourself on if that will happen spontaneously or non-spontaneously. Tap out. Lonsdale, your turn.
Welcome back. This is page 920, and it's the summary for the 4 scenarios of enthalpy and entropy changes. And I wanted you guys to take a look at this and to copy this into your notes as well. And the reason for that is it's a great summary table of will a reaction take place or will a reaction not take place. So if you look here, we have delta H, meaning it's endothermic, it's bringing in energy, which is delta H greater than 0, or delta H less than 0, meaning it's exothermic, meaning it will produce energy. So these are those columns. And then here, we have increasing entropy, so delta S, the entropy is greater than 0, or decreasing entropy, the delta S is less than 0. And what it'll do is if you have an endothermic reaction with an increasing entropy, the delta G is less than 0 at a high temperature, or the delta G is greater than 0 at a low temperature. This process is spontaneous at high temperatures. So what this is telling you is that it's an endothermic reaction, which means it's going to be bringing in heat from the environment. So at a high temperature, that reaction will spontaneously happen. For this one, in an exothermic, well, you're increasing the entropy. Delta G is less than 0 at any temperature. The process is spontaneous at any temperature. So if you have a high amount, or if it's exothermic, which means it's going to be releasing energy, and you have a high amount of energy that is in the system, it's going to just happen. For this one, if you have an endothermic reaction where you are decreasing entropy, the delta G is greater than 0 at any temperature, therefore the process is non-spontaneous at any temperature. So this is not going to be happening at any temperature. And then finally, for the last one, the delta G is less than 0 at low temperatures, the delta G is greater than 0 at high temperatures. The process is spontaneous at low temperatures. So it's an exothermic reaction with decreasing amounts of energy. So it will happen spontaneously at low temperatures. So these are reversed, and then these two are reversed.
At recording.
So what this means in terms of the actual math, and the actual math can be found on page 923, sample problem 16.11. And it says calculating delta G under non-standard conditions. So we've talked about all of these things being at standard conditions, and now we're going to talk about them at non-standard conditions. So we're looking at something where it's not 1 atmosphere, where the temperature is not 0 degrees Celsius. So all of these things being non-standard. And the equation that we use is a 2-part equation. The one in the book is this. Delta G, or change in Gibbs free energy, is equal to the Gibbs free energy naught plus RT ln Q. So that's what's in the textbook. What's going to be in your AP test is this. Delta G is RT ln K and it's a negative. We're not going to explain how to get from here to here. That's going to be a second video that Anderson is going to attach to this one.
Mm-hmm.
So that way you'll watch that, and it does a really amazing explanation of how this whole thing works. So for now, this is where you're going to get to. This is where we are now. What you should note in terms of the differences is that this is the same. This gets taken out. This becomes a negative, and the Q and the K change. Really, they mean the same thing, they're just using two different letters. So going back to the one that we're talking about in the book, because it's a great basis for this. So I know what you're thinking right now. You're thinking, Lonsdale, you're teaching me something that's not on the AP test. True, but this is the basis for what is on the AP test. So this is point 1, and then the next video is going to give you 1.0. Hint, hint, nudge, nudge. So, looking at this problem, it says, what is the free energy change for the process shown here under specific conditions? Those conditions being a temperature of 25 Celsius, which we can then calculate out to be 298 Kelvin. The pressure for the nitrogen gas is 0.870 atmospheres. The pressure for the hydrogen gas 0.250 atmospheres, and the pressure for the ammonia is 12.9 atmospheres. The overall equation, like I said, is this. The balanced chemical equation is 2NH3 in gas state becomes 3H2 in gas state plus N2 also in gaseous state. This will become important later when we get to how do we talk about that Q. And of course, our final is the delta G naught is 33.0 kilojoules per mole.
Beautiful.
So now, thank you. Now, we're going to look at this in terms of this equation. And I'm going to do some things that may seem like magic, but I promise they are not actual magic. Sorry, Rex. So the first thing, we are solving for delta G. That's what we're solving for. Is equal to delta G naught. We know that, which is 33.0 kilojoules per mole. This kilojoule is going to become important later, so keep that in mind. And that is plus, and here's where we get into a lot of numbers, but really it's not that much, plus R. We know R is the gas constant. And in this case, it's 8.134 joules per mole Kelvin. Okay, so now we've noticed a discrepancy. We have a joules here, I'm going to make my J a little bigger, and a kilojoules here. So for now, I'm going to leave it, but we're going to have to either convert this to joules or convert this whole thing to kilojoules later. And we'll talk about that when we get there. And then that is multiplied by the temperature. The temperature is 298 Kelvin. Hey, brilliant. The Kelvins cancel, which is awesome. And then that's multiplied by Q. Well, sorry, the ln of Q. And so the ln of Q, this is where these numbers seem magical, but they really aren't that magical. So if we take a look, we have 0.250, 0.870, and 12.9. What we're looking at in this case is we're looking at Q equaling the concentration of reactants, over the concentration of the products.
Sorry, Lindsay. I think we're reversed, actually.
Did I reverse it?
Yeah, it's reversed.
Oops.
It's all good. I would have done the exact same thing.
Products. Oh, yeah, that makes sense.
Yep.
Apologies. Thank you for catching that one, Anderson.
All good.
Thank you. So it's the reactants. Nope. It's the products over the reactants. Ignore the part where I started with reactants. I was wrong, and then just ignore it. So when we do concentrations, well, we know a couple of things. One, We know that the atmospheres is going to be telling you essentially how much there is, but and we're looking at it for the reactants and the products. And so what we need for our Q here is we need the concentration of the hydrogen times the concentration of the nitrogen all over the concentration of the NH3. So when I do this, I look back and I say, okay, what is the concentration of hydrogen, or in this case, what is the pressure of hydrogen? It's 0.250 atmospheres. So I got 0.250 atmospheres times 0.870 atmospheres. Okay. And the 0.870 comes from the N2, and then that is all over the wonderful products, or reactants in this case, 12.9 atmospheres. So when we do this, the atmospheres are going to cancel, which is great, so it doesn't really matter in that case. But we still have to take into account the fact that we have made 3 moles of the H2, and we had 2 moles of the NH3 to begin with, and only 1 mole of the N2 gas. So that's where, if I look at this was my hydrogen. Hydrogen has 3 moles, so it's cubed. This one here, nitrogen, had 1 mole, so that we don't have 1 here. And then for NH3, it's 2 moles, so you square it. And you're going to take the ln of that entire thing. Alright? So if I look at this, I have lots of brackets, lots of math, lots of amazing things. But essentially what you're going to end up doing is you go electronic brains, type. You end up with a number. And the number that you end up with is going to be one of 2 things. It's either going to equal out to 9680 joules per mole. Let's make sure I can do this, right? The kelvins canceled, we have joules and moles. The atmosphere is all canceled, so we're good there. Or you're going to end up with 9.68 joules per mole. But instead of being a joule, it's a kilojoule. So it's times 1,000. So it doesn't really matter if you convert this to kilojoules or you convert this to joules. Either way, though, you have to do it before you add. If you do it after you add, you're going to end up with the incorrect answer. So it's got to be before you add to make sure your units match. Kilojoules and kilojoules, or joules and joules, and either is fine. So, what's going to happen now, you're going to watch another video that's about 5 minutes long from a wonderful British man who talks through IB, and IB is essentially the equivalent of AP. They're about the same thing. Explaining how we get from this equation down to the equation that you have in your AP test. And then all of this, we'll be working on problems on Tuesday and Thursday, and so we will see you after you watch this video Thursday in class. Have a great one.
Woohoo! Bye.
Bye.
So I struggled with this one a little bit, and let me illuminate those struggles for you. This equation, you don't need to know it, it's not in the data booklet, but I think it helps. The delta G on the left, when that's 0, you are at equilibrium. And therefore Q, the reaction quotient, turns into Kc, the equilibrium constant. And rearrange that to get delta G theta equals negative RT ln Kc. Now, rather confusingly, the equilibrium constant is K in the data booklet. Now, this is what confused me. The books say that delta G theta equals 0 at equilibrium. But here's the problem. If you set that to 0, you can't really solve that equation. I'm going to get infinities and zeros myself. So you know what? Delta G is 0 at equilibrium, but this is delta G theta. And that isn't 0 at equilibrium. Okay. So I can solve it for that. So what are the tricks? Well, temperature's in Kelvin. The gas constant involves joules. And the change in Gibbs free energy involves kilojoules. So you need to keep your eye on that for a unit conversion, if necessary. So the position of equilibrium depends upon minimizing Gibbs free energy change and maximizing entropy. That seems to be as much as you need to know, and I trust the Noose book on this. Oh, I spelt position wrong. I got the position of the S wrong. There are graphs like this in some of the other books. I'm not convinced that you need to know these graphs for the IB. I think that's more than you need to know. I trust Noose. Okay, so the only Kc value that you know is for the dissociation of water, and it's 1 times 10 to the minus 14. So what can we do with that then? Well, if I tell you that delta G theta for that reaction is 79.9 kilojoules per mole, can you work out the value of the gas constant? So rearranging for the gas constant R. Alright, I'm going to convert delta G theta into joules because I know that R is measured with joules. Temperature, this is assumed to be standard conditions, so 298 Kelvin. And it comes out at 8.32. Let's just check the value in the almighty data booklet. 8.31. Okay, so it works. That's not bad considering we were using 1 sig fig for kW. Okay, let's try another one. Calculate the value of the concentration of ammonia at equilibrium given the following information. Well, I suppose we better plug and chug that into our equation. Delta G theta is negative RT ln K, and I can get the equilibrium constant because I got the equilibrium equation. Alrighty, I'm going to stick to joules. So I've multiplied my delta G by 1,000. Temperature in Kelvin, and solve for ln K, and then K. So that gives me ln K of 13.37, but I really want K, so on your calculator press inverse ln, and you get K is, well, I'm going to keep 3 sig figs because my question has 2 sig figs, and I'm going to keep 1 extra and then round off at the end. Alright then, so K is 63,800, and I'm going to write out the equation for the equilibrium constant, put in the 2 numbers that I have, and solve for the third number, which is the concentration of ammonia. So the concentration of ammonia ends up at being 3.6 moles per decimeters cubed. And that makes sense to me. Kc is bigger than 1, so there's probably going to be more ammonia than there is the other chemicals.